Hi, I'm Oleg, and I will present simple and effective VAE training with calibrated decoders. Variational latent variable models have enabled powerful image generation, feature prediction, and representation learning. However, they're often hard to train, and practitioners often resort to extensive tuning of a heuristic hyperparameter beta. In this work, we analyze a simple fix that in practice leads to good performance while not requiring tuning this heuristic weight. Let's focus on variational autoencoders, or VAEs, which encode an input into a representation and generate it back. At a high level, VAEs learn to reconstruct the data, such as with an MSE loss, and reduce the representation complexity with a scale divergence loss. To balance the losses, many practitioners use a heuristic weight beta in a method called beta VAE. When the beta is too low, the generated images are unrealistic, while if the beta is too high, the images are blurry. Practitioners know that beta is a very sensitive parameter and needs to be tuned for every new dataset and architecture. Further, beta VAE does not correspond to a valid evidence lower bound and cannot be used to measure log likelihoods. To see if we can eliminate the hyperparameter beta, let's take a look at the evidence lower bound, or elbow. We define the encoder as a distribution and use its likelihood as the reconstruction term. Gaussian decoder yields the MSE loss with another term that's dependent on the variance. This reveals the drawback of the MSE objective. Without taking into account the variance term, the decoder cannot represent its confidence, and it will be uncalibrated in a statistical sense. Instead, we can learn the variance end-to-end with this full elbow. Observe that the variance of the decoder serves as a balance weight between the two losses. This is similar to beta VAE that tunes this balance weight manually with direct correspondence between sigma and the beta. The elbow derivation provides a way to learn this balance. The sigma has to be adjusted to minimize the MSE term, but also cannot grow too large because of the logarithm penalty. We call this model that learns the variance of the decoder sigma VAE. We know that the idea of learning the variance goes back to the original VAE paper. However, recent applied work has generally avoided it in favor of the simple MSE objective and beta VAE. In this work, we provide an analysis of various calibrated decoders and further propose a novel analytic variance scheme for VAE training. Why is it important to learn a calibrated decoder? Consider a simple latent variable model such as a Gaussian mixture model with constant variance that is fit to one-dimensional data, here shown as black dots. For high variance, the Gaussians will collapse as they become too wide to specialize in different data points. For low variance, the Gaussians will be too sharp and overfit. As we saw already, the same phenomenon happens in VAEs. Here, if the decoder variance is too large, corresponding to a large beta, the latent dimensions collapse and the samples become blurry. With a small variance, the samples might become unrealistic. In contrast, learning the variance produces high-quality samples on all datasets. This also works on a model trained for stochastic video prediction of robotic arm movements. The sigma VAE powered model produces good videos, while the naive Gaussian VAE removes the arm from the image as it is not able to retain the information about the arm position. In the paper, we also show that optimal sigma VAE achieves a sweet spot in terms of information in the latent variable and the divergence between the marginal and the prior. If learning the sigma works so well, why is it not used more often? To answer that, we provide an analysis of various calibrated decoders. A naive approach is to predict a different variance for every pixel as another decoder channel. While this is an expressive decoder, empirically, we find that it leads to poor samples. The FID perceptual distance is much higher for the per pixel sigma VAE, even worse than the naive unit Gaussian. More generally, while learning the variance is beneficial, learning more expressive variance, measured as the number of learned variance parameters, monotonically leads to worse FID and larger marginal divergence. Instead, we can train a single shared variance. This method empirically works better. However, optimizing the variance is still a challenge. We can use gradient descent, but stable training and fast convergence often require careful learning rate tuning. We can improve this with an analytic estimate in a novel algorithm that we call optimal sigma VAE. The optimal variance is simply the average MSE over the dataset, which we estimate from the current batch. This method converges faster and achieves superior likelihood. Quantitatively, we evaluate different calibrated decoders on evidence lower bound and FID distance. Overall, the naive unit variance Gaussian VAE works poorly, while the calibrated decoders generally work well. Sigma VAE versions are comparable to the manually tuned beta VAE and sometimes even better, and the optimal sigma VAE tends to be the best. In summary, we show that calibration is essential for good performance. Single shared variance requires careful setup but performs best without requiring hyperparameter tuning, and using the optimal variance estimate improves optimization. In the paper, we have more analysis and other tips on training VAE models. Check out these details and the open source code in both PyTorch and TensorFlow on our website.